Okay, so the big picture of the maps and matrices thing is this. For every map can be represented with a matrix. Every matrix can be represented with a matrix in a particular basis. In other words, when you choose a matrix representation of a map, it's always going to be in a particular basis. Now, given every matrix, given a basis, represents a map, a linear map. Every linear map represents a linear. So something about matrix. Now, the point is here, this gives you the crucial sort of context of matrices. Now, if you remember, we started with a linear system, right? As a bunch of equations. And we could represent that. The ordinary matrix was just bookkeeping to solve it with the gaseous method. We can represent this as a matrix equation where you have some matrix here times the vector of variables equals the constant b. So, for example, 1, 1, 1, 0 times x, y equals 1, 2. There's an example. And so that in this picture we can think of this matrix as being a map from any vector. It takes any vector in the space, and it's going to map it. If you look at all the solutions, if you put in different x and y's here, it's going to map vectors. Every vector here is going to get mapped to some other vector. So this linear system says how many vectors get mapped to this vector. If I just look at this just the multiplication of a matrix onto a vector gives another vector in a vector space. So we can sort of set linear systems in the context of maps and matrices. We can set it sort of in this context. Now, before we defined the rank of a matrix. Okay, so the rank, say, of M here, well, it's going to turn out that the rank of M is also the rank of every map that it represents. Okay, so we have to sort of deal with this more. This is sort of the big picture, that everything's going to work out so that if we wanted to answer some of these questions up here about the matrix, and you know how you had to find the range space and null space and find bases, well, it's going to be easier in some ways to say find the matrix for a map and then just ask, well, what's the rank? Because the rank is going to be the number of non-zero rows of the matrix after you get put it into echelon form. So you can find whether a map is onto depending on whether by finding the rank of the map. Now, since we know that the rank plus the nullity equals domain, if we find the rank, we can find the nullity. So just by finding the number of non-zero rows in a matrix that represents a map, I can find whether the map is onto and one-to-one. or how badly it fails to be onto and one fails to be one-to-one. And of course, it can be one-to-one and still not be onto, or it could be onto and still not one-to-one. So, but I can find the rank of the nullity from this equation, and then you can see what's going on. So this takes us back to that connection. So the question is this: what is given? So we have before. We've had two ways to find maps. We have for example, we can find and we can define a map by a formula, say f, where we say f of, take, say, a vector x, y, to 2x plus 2y, x minus y, say, okay? And we also said we could define the map. In fact, the same map, well, we could define a map. This could be a different map. We would take 1, 0, 0, 1, and this is a basis for this two-dimensional space. We're doing this example in R2C. We can just give any particular values here, 3, 4, say 1, 1, okay? This gives you a basis action. And this defines a map. So I can go back and forth, right, between these two representations of, if you're given the basis action, you can find the general formula. And if you're given general formula, you can find the basis action. You find the basis action just by choosing x to be 1 and y to be 0, and 0, and you could x to be 0 and y to 1, and so these things would be special cases. These are not the same maps. Let me call this G here, okay? Well, so we have a third way to specify the map, which is by finding a matrix. We're going to, for the map G here, we're going to write capital G for the matrix. This is going to be the matrix that represents this map. Now, how is it defined? Well, it turns out the matrix is defined as the vectors in the basis action. So it's just going to be 3, 4, 1, 1. So for this map that's defined by this basis action, we have 3, 4, and that's the matrix. You just take the column vectors here. Now, this is going to be a little, we have different bases, a little bit more complicated. This just happens to be standard basis to standard basis, right? Because what the map here is G is from R to C to R to C, and it's like standard basis to standard basis. So if we wanted to find a matrix in different bases, we're going to have to do something a little more complicated. But this is the basic idea. It's still going to be, we find the image of the basis vectors. So if I have a different basis vectors here, I still just find the images of these different basis vectors. Now, let's say that I wanted to find the matrix F that represented this top map here, F. What is this equal to? Well, we find the basis action for F. We say 1, the standard basis, say, is 1, 0, would go to x is 1, y is 0. Well, that would be 2, 1, right? Because the y's would be 0. And the other one would be 0, 1, would go to where x is 0 and y is 1. That would be 2, minus 1. So therefore, F would equal 2, 1, 2, minus 1. Now, we can see that this works because if we take F times an arbitrary vector, that's going to equal 2, 2, 1, minus 1, xy equals, and be 2x plus 2y, and x, you see, 1 times x plus minus 1 times y is x minus y. So it turns out that matrix multiplication exactly sort of, and this wasn't by default. I mean, this was when people define matrix multiplication, this was sort of part of why they wanted to define it that way. But you can see I've recovered the formula. So I can go back and forth. From the matrix, I can find the basis action or the general formula. From the general formula, I can find the basis action in a matrix. From the basis, so there's three different representations now. I could find them from any, I could find any of the three representations from any of these. I could find any of the three representations from any of the other ones. Okay, so you could say, well, is F 1-to-1 and onto? Well, we could go and look at the general formula like we've done before, or we could take F that is, say, 2 to 1 minus 1, and see, so is the map F 1-to-1 and or onto? Well, we can take this and we can do minus 1/2 row 1 plus row 2, right? And that's going to give us minus 1/2 is minus 1 plus 1. Well, it won't affect the top one, but we'll get a 0 there. And then minus 1/2 is going to be a minus 2 there. Okay, so the rank of F is going to equal 2. Okay, now we have to sort of show that the rank of F, of capital F, equals the rank of lowercase f. But if this was true here, then we know that the rank of, that means the dimension of the range space was 2, right? This is dimension R for F. Well, that would equal 2, but that's equal to the dimension of W here, which equals R2C. So F is onto, right? And since rank plus nullity equals the dimension of the domain, which is 2, and since the rank of 2, the nullity is 0. So F is also 1-to-1, meaning that this map F here is an isomorphism between the two spaces. So we didn't have to go through and sort of say, okay, well, let's take the range. We could verify. We could go through and verify that the range space was that way. So it's important. So that this result here is sort of like a really useful result, that the rank of the map equals the rank of the matrix. And so, well, let's see. Let's look and see where we are in this one, this maps and matrices chapter. We have the action of linear maps. So it goes through and it shows, but this is showing you there's many different cases, right? If we have standard bases, then it goes through and motivates this whole what's going on in terms of the map sort of being produced by matrix multiplication. And one of the things in this chapter that you'll notice is, if you go through it, is that it doesn't assume you actually know what matrix multiplication is. So there's a lot of extra material here because it tries to introduce and motivate matrix multiplication as the thing that produces these kind of matrix maps. So it goes through lots of examples here trying to motivate this. And these are all examples of finding the the matrix. So here's the general definition. Suppose that V and W are vector spaces of dimension n and m with B and D with bases. So the basis of the domain V is B, and the basis of the codomain W is D, and you have a linear map. Okay. So now if the image of the betas are the basis vectors in B. So you have to take the image under H of the n vectors in the domain. But then you have to take them in basis D. Now remember, we sort of said, okay, one of our homework problems was you're given a vector and you want to represent it in a given basis. So when I just compute H of beta 1, it might not be in basis D. So I'm going to have to convert it to basis D, and we'll do that. But so if I'm given this, then I take the vector here, the image of the first vector in the basis B, in the basis D, and that's the first column matrix. The image of the second vector is the second column. So the matrix that represents in basis B and D, the map H, is the matrix of these images of the basis action. So apart from this sort of issue of the bases, this is exactly what we had before. If these are the standard bases, if these are the same ones, then you just get this and it works simply. Okay, so there's lots of examples. And then let's see. And this is about sort of when you multiply a matrix times a vector, you get the image of that vector in the basis, the codomain basis. Okay, so, and it's motivating this is the vector product. So it's saying, okay, we didn't assume that you understood matrix vector multiplication. So there's a lot of this chapter that you already know. So you have to sort of go through and just see the pieces that you want that you don't have to go through and see, relearn. And this goes the other way. It shows that we just did this, any matrix represents a linear map. We will show that too. But I wanted to get to this thing, linear map of a matrix. Okay, here's the theorem I want to get to. This is what I just quote you. The matrix ranks equals the map rank. Okay, the rank of a matrix equals the rank of a map that it represents. And there's a proof here that goes through and argues, and let's just sort of review that. But let me